Welcome, this is lecture number 26. In this lecture, we are going to talk about state space averaging technique. First, I will consider state space modeling of a simple RLC circuit. Then, I will show the dynamics of switch mode power converters, state space averaging technique, and then finding linearized small signal model and DC operating point. So, first the important definition state variables in if we consider like any RLC circuit, that means if there is any energy storing element in electrical circuit like inductor and capacitor, we generally consider the current through the inductor to be one state variable which is IL and the voltage across capacitor to be another state variable which is Vc. So, here IL is considered to be x1 and Vc is considered to be x2. Next, the state vector, if there are more than one state are there, then we consider them in a vector format and that we call state vector. Then we can write down the state space equations for a given dynamical system, where it can be we can represent a first order as well as higher order dynamical system, and the state space representations for a higher order dynamical system we write, suppose if the system order of the dynamical system is n, then we write n first order differential equation and that we write in terms of state space representation. So, we write in terms of A matrix and B matrix, where A is x is the state vector and u is the input vector. Similarly, we can write also output vector in terms of state vector and the input vector, where u is the input vector and y is the output vector. If we take a RLC circuit, it is a series RLC circuit where we are considering here the inductor current to be one state and the capacitor voltage to be another state, and we have taken the polarity of this voltage accordingly. Now, if we write KVL equations, then the first thing L di like what is the inductor current? The inductor current is passing through this capacitor. So, which is C0 into dVc dt. This is one equation. Similarly, what is the inductor current dynamics? That means, if we take the voltage across inductor, this is my VL. What is VL? VL is nothing but L dIL dt. And if we write the KVL, the full equation, so V in, then this drop across this resistance R into IL, then L dIL dt is the VL, that is the drop, and minus Vc, which is the capacitor voltage, and we can add up to 0, the whole. Then this series RLC circuit, if we write the state space equation, where we have considered the first state to be capacitor voltage here. Here we have taken state 1 to be capacitor voltage and the state 2 to be inductor current. So, we can write in terms of A and B matrix, where A matrix consists of 4 elements 0, then second element, then this third and fourth element. So, these equations we already wrote in the previous slide and we can just plug in to write in terms of. So, that means we can write something like x dot equal to A into x plus B into, in this case it is V in, which is a supply. That means, it is the input to this particular RLC circuit. Similarly, we can write output equation. So, here output we have taken output voltage, which is same as the capacitor voltage. So, it is simply 1 0 of the state vector, right. So, we are taking x2 as the output, x1, because x1 is nothing but the state variable 1, which is the capacitor voltage. That means, it is nothing but the capacitor voltage. The next part, the state space for pulse width modulated converter or pulse width modulated converter. So, consider a PWM converter with 2 sub interval. That means, in this switching converter, whether it is a you can take a buck, boost or any other converter, in continuous conduction mode, generally for hard switch converter like a buck and boost, as well as buck boost. So, we will get two switch state, switch is on and switch is off. If there is only one controllable switch, then we are getting one state when the switch is on, which is state 1, and the switch is off, state 2. And we are talking about pulse width modulation, where the total time period is constant and the on time is nothing but d into Ts. Each interval represents a RLC circuit and we will take it. Now, we want to compute the total overall state space equations of two sub interval. So, we have to write down the sub interval 1, sub interval 2. For each sub interval, we have to write the dynamical equation and then we need to arrange in the state space format. Okay? Then we will find the state space model should be different for two sub interval, because if they are identical, then there is no switching action, right. Now, first of all, before we move forward for state space averaging, we need to understand the power spectrum in switch mode power converter. So, switch mode power converter, we provide a gate signal Q. In under pulse width modulation, we generally consider a duty ratio D, and we have already considered, that means if we take the power converter, this is our duty ratio, this is our D into T, and this we take total time period to be constant, and we are talking about this. Now, this time period is constant, that means it is a periodic signal, but this duty ratio also we can apply a small perturbation, that means the duty ratio can also have a sinusoidal excitation. Along with the steady state value D, we can also inject a small amplitude sinusoidal excitation with this duty ratio. Now, where the amplitude of Dm, that means excitation amplitude, is much smaller than its steady state value. Okay? And omega m we are assuming, that means the excitation signal, the frequency, we are basically trying to sweep this frequency from 0 frequency, slowly we are increasing, but this frequency, that is the modulating frequency, is much smaller than the switching frequency. Then if we draw the waveform of this converter, where this is the gate signal, for our case it is Q, and we can draw corresponding switching behavior of the converter. So, this can be a inductor current, this could be inductor current. Now, where if the ripple is small, then we can neglect the effect of the ripple and we can straight away take the average dynamics. But how far this average dynamics is valid? If you draw the power spectrum of this converter, where we have considered a periodic signal Q with time period T, that means if we take omega s, it is 2 pi by T, where T is the time period. That is my switching frequency in radian per second. And we also have a modulating frequency, because the gate signal is modulated using a sinusoidal excitation. Then what will be the resultant frequency spectrum of this gate signal? So, it has two things. One thing, we have this gate signal is a periodic signal, which actually periodically occur in every time period T, but in this gate signal we have one duty ratio term, and that duty ratio also we are varying. That means, it is a frequency modulation, where we are modulating the duty ratio with the frequency, modulating frequency omega m, and we also have a switching frequency. And if we draw the power spectrum of the output voltage, first there will be a large component of the DC quantity, right? And along the DC quantity, we will also have some component right side and left side as a modulating. This is a DC component, which is omega, that means equal to, that means here omega equal to 0. And since we have also injected one sinusoidal excitation, So, it will also have a side lobe and which is omega m. Similarly, we can draw the omega minus omega m left side, but I am not drawing in the left side. Then omega m, it will be twice omega m and so on. So, side lobe will be created because it is a frequency modulation. Same thing is applicable. So, here if you do not modulate this signal, if you skip this modulating signal to be 0 frequency, that means it is simply a periodic signal with a fixed duty ratio, and there we will get the component as a fundamental like a DC component, switching which is a fundamental component, their harmonic which is 2 omega s and so on. But since we are also injecting another low frequency excitation, so on top of this switching the DC component, switching frequency and harmonics, we will also have side lobe which will be created by the modulating frequency. This will also have a side lobe. Now, if the omega m is much smaller than omega s and that we have considered, then these side lobes are almost close to the is corresponding this component, that means the switching frequency component. Okay. Now, if we can show the dynamics, because we are interested to obtain the behavior of the system, if we excite with a modulating frequency omega m, we want to see what is the effect of the output. That means, if we excite the duty ratio with a omega m sinusoidal excitation, we want to see what is the effect in the output voltage corresponding to that particular frequency, because we want to generate or we want to derive a linear model, linear time invariant system, that LTI model. And we know for an LTI system, if we excite with an omega m frequency, then the output should also contain only that excitation frequency only. The other frequency should not present in a linear system, but it is a switching converter and we want to get an approximate linear model. That means, we are interested to obtain what is the power spectrum at the excitation frequency. Okay. So, this is sideband we have discussed and the switching harmonics. Now, under state space averaging, what we are doing? So, we are assuming that our averaging is valid for low frequency and under this particular assumption, that means the excitation signal amplitude is much smaller than the original DC quantity and the excitation frequency is also smaller. So, we can ignore the behavior of the ripple information. So, we are only considering the average dynamics of this converter. So, under this condition, we can move forward with the state space averaging. So, this requires the assumption the ripples are negligible compared to the average dynamics, or the ripples are very fast, or this is the assumption where the switching frequency is infinitely fast. So, if the switching frequency is infinitely fast, that means this particular frequency will move farther right side, far away, and then we can simply extract the information corresponding to omega m. We can extract. Okay. Now, in state space averaging, we will write the equation of subinterval 1, which is valid for the time period of d into t, and subinterval 2, which is activated during 1 minus d into t, and then we can obtain this is the average quantity. In fact, we will use this x bar to be, it is represented in terms of x, which is average over a cycle time period t. Then we can write x dot, that means we can write x dash should be equal to d into a1 plus 1 minus d into a2 x plus d into b1 plus 1 minus d into b2 1 minus d into b2, all right. into V in bar. These are the average quantity, okay, and that we are considering this to be denoted as F average. Okay. Similarly, we can write y bar is equal to d into C1 plus 1 minus d into C2, this whole thing to be x bar. Okay. Now, state space averaging, first we need to consider perturbation. That means, we talk about x bar, which can be written as capital X plus small perturbation. That means, we have seen earlier that if we take the original duty ratio, it consists of two parts. One part is capital D, which is a steady state quantity or the fixed quantity, plus some AC excitation, and which we are taking as a x hat. It can be AC excitation, it can be step excitation. So, we are talking about x hat, because in frequency response we are assuming this x hat will carry, because it will be the injected sinusoidal signal and we want to get the approximate linear model. So, all this notation, it is represented here. The assumption is that we told earlier that all this perturbed quantity, if you take the magnitude, it should be much smaller than its steady state quantity. That is the assumption. This is true for all this quantity. So, that means their corresponding magnitude of this should be much smaller than the capital V. Then, in order to obtain the linearized model, we have to write the Taylor series expansion, which means this is the original model, and we wrote that x dot is nothing but f into average, which is a function of x dash, comma V in dash comma d, right. Then we have to obtain the perturbed model, and which is by applying Jacobian. How can we find out F average under steady state? So, what is our F average? Here our F average, we know that it is d into A1 plus 1 minus d into A2 x average plus d into B1 plus 1 minus d into B2 V in average. Okay. So, this quantity we know. Now, under steady state, we need to consider that d should be under steady state. That means, if we take steady state, this should be replaced by capital D, x should be replaced by capital X, and V in average should be replaced by capital V in. That means, F average under steady state should be equal to what? Capital D A1 plus 1 minus D A2 x plus D B1 1 minus d B2 V. This is a steady state quantity, and it can be shown that this quantity will eventually become 0 vector, because under steady state this can be proved that this will be 0, because their derivative part is 0. So, if you take the derivative of x dot is 0, and this gives us this equation. That means, we can solve, and if we take this to be A matrix and this to be B matrix, then we can solve x equal to minus A inverse B into capital V in. This can be solved, where the A inverse, the A must be non-singular, it must be non-singular, and this is true because this A matrix average quantity can be shown to be non-singular, and then only we can find out uniquely the two steady state point. That means, what is x? So, X consists of two parts, the average inductor current and the average capacitor voltage. So, these two can be uniquely characterized by this equation if A matrix is non-singular. Now, we have to find out, that means I told you. So, this quantity we can find out by this, and also correspondingly we can find out V 0, because we know d into C 1 plus 1 minus d into C 2 into x is the average value. So, you can find out from here what is my average or steady state voltage. Now, the next part we need to do linearization, and we discussed that this term will eventually become 0. Okay? The next part, this part is 0, and if we want to do Taylor series linearization, the higher order term consists of x hat square, it will also consist of d hat square and so on. It will also consist of v n hat square and other higher order term, and we are ignoring, we are assuming this perturbation square or the perturbation products are neglected or negligible. So, under that assumption, this can be dropped, or this quantity, that means x hat dot, can be approximated as dou f average dou x in this case into x hat plus dou f average into dou d. This is computed at steady state, this is computed at steady state into d hat plus dou f average into dou v in computed at steady state into v in hat. So, this can be approximated when we ignore the higher order term, that means the perturbation of the duty ratio, perturbation of the state variable as well as the perturbation of input voltage should be small enough compared to their steady state quantity. And I will show you in subsequent lecture that this assumption makes this small signal model to be valid within a narrow bandwidth, beyond which this model is not valid, because the perturbation will no longer remain small. Now, the next part, how do you find out f average? So, what is f average? If we write f average, we know it was d into a 1 plus 1 minus d into a 2 x plus d into b 1 plus 1 minus d into b 2, this into v. So, you can write further, we can take it a 1, that means we are taking this term and this term, minus a 2 into x into d plus a 2 x 2 plus b 1 minus b 2 v in into d plus b 2 into v, because this term and these terms are accumulated to get this term. Okay? Similarly, this term and this term is accumulated to get this term. Now, then if we want to find f a v dou f dou x at steady state, from this equation we can straight away write that this is simply d into a 1 plus 1 minus d, because it is under steady state. Okay? Because this is, we are differentiating with respect to this quantity and it is under steady state. Okay? And this we represented by A matrix. Okay? Now, what is dou f a v by dou d at steady state? Okay. So, here we can do one thing, let us okay, because let us not take the steady state directly, because we can find out the steady state first, let us derive. So, if we write down from this equation, if we write down from this particular equation, we are differentiating partially with respect to this quantity. So, initially we are assuming that we are not talking about steady state. That means, what is this quantity? We are partially differentiating. So, it will end up with dou A 1 plus 1 minus d into A 2, because we are differentiating with respect to this quantity. That means, if we want to write what is my dou F phi by dou x at steady state, then we will simply replace this duty ratio to be its steady state value. So, it will be d into A 1 plus 1 minus d into A 2, and this we represented as A matrix. That means, this we represented by this matrix. Okay. Now, next part again we are writing. So, what we are writing again? Again we are writing, we wrote in the earlier equation f a v was, this part already we took 0, right. This we have ignored, right. So, we have ignored this part, we found it is A matrix in the previous equation. Now, what is f a v? We saw it was A 1 minus A 2 into x average into d plus A 2 into x average plus, we separated B 1 minus B 2 into V in into d plus B 2 into V in. Now, we want to find out what is my dou F average with respect to dou duty ratio. So, you want to only consider these two terms, which consist of d duty ratio, other two terms are independent of d. So, we will find out A 1 minus A 2 into x bar plus B 1 minus B 2 into V in bar. That means, if we take the steady state value of d under steady state, the states and the input voltage will be replaced by their steady state quantity. So, you will find out that A 1 minus A 2 into capital X plus B 1 minus B 2 into capital V in, and this quantity we denote as B 1 1. So, this quantity we denote as B 1 1. Now, how can we find out B 1 2? So, you can find out dou F A V, dou by the same method. If we write down under steady state condition, what will be this? So, from this expression we can clearly write that it will be only the last term. That means, we will get d into B 1 plus 1 minus d into B 2. This will be my V in, and this is represented by B 1 2. All right. So, that means, we can find out A 1 1 this term. So, what is my A 1? We found A equal to d into A 1 plus 1 minus d into A 2, that was our A 1, correct. What was our B 1 1? We found it is, so if you go to the previous slide, B 1 1 A 1 minus A 2 into what x, right? Yes, A 1 into x plus B 1 minus B 2 into V in. And what is B 1 1? So, if we find B11, sorry, B11 is what? B12, it is simply d into B1 plus 1 minus d into B2. So, with this we can write all this, and this B2, it is a 2 into 1 matrix, 2 cross, this is also 2 cross 1 matrix, this is 2 cross 2 matrix. Okay. Now, this whole thing which is a B matrix is a 2 cross 2 matrix, and this is also 2 cross 2 matrix, this one. So, now after writing this per term model, where we have ignored the higher order term and the DC offset term was 0, set to, because under operating condition FAV, we wrote that FAV steady state was a null matrix. Then we got this linearized per term linearized model, and now we can apply Laplace transform. So, we can apply Laplace transform to find this transfer function. Okay. So, x of s hat x si minus A inverse into B to this. So, we can derive the small signal model x of s in terms of si minus A inverse of B to D. Then we can, what is x hat of s? It is IL hat of s, Vc of hat s, capacitor voltage, and the output voltage is nothing but C into x of s. So, it is C into Si minus A inverse B into this term. How can we obtain now using this model? These two models we have already discussed. How can we obtain control to output transfer function, which is GVDS? That means, it is the V0 s, all will be s, by d hat s, V0 hat s by d hat s, which is obtained without considering any perturbation in the input voltage, because it is control to output transfer function, where we keep the input voltage constant. Then you see this matrix here, there are two terms, one is d hat and v in hat, but we want only d hat. So, we need to multiply a column vector which is 1 0, because we want to extract only this term. Similarly, if we want to talk about audio susceptibility, which is V 0 by S, V 0 hat by S by V in hat by S, and in this case we are taking the duty ratio to be constant. That means, it is under fixed duty ratio operation. So, you can straight write CSA, whatever it is there, that means V 0 this. With this we have to multiply 0 1, because we want to extract this one. So, this one, it is just the other, here we extracted d hat, here we extracted V in hat. Okay. So, these two things we have extracted. Control to inductor current transfer function GIDS, which is ILS by d hat s, and where we are considering the input voltage perturbation to be 0. Here it is the same model here, but we want to take this one and this one. That means, the first case we have to write a row matrix 1 0 and then a column matrix 1 0, then we can write down from this. That means, we can derive control to output transfer function, audio susceptibility, control to inductor current transfer function, everything that we can derive from this transfer function. Now, the state space averaging of a synchronous buck converter, it was the method I have discussed, how to start with a state space model of a DC-DC converter using two sub interval dynamics, and from there how can you obtain the average model, and from the average model we can apply Taylor series to extract the small signal model, as well as we can find the equilibrium point. Now, in the practical DC-DC converter we have two sub interval, switch on and switch off. This we are talking about in continuous conduction mode, because we are using synchronous configuration. Then we can write down the equation under individual configuration. That means, when the switch is on, what are the state equation, right, and the output equation, and we are taking a inductor current to be one state x 1, that means our x 1 is IL and our x 2 is V c, right. Then we can consider sub interval 2, where the switch is off, main switch, but this complementary switch is on, it is on. Under this condition, again our state variable is I L and x 2 is equal to V c. So, you can write the state space equation from this subsystem dynamics. Then the overall state space model, that means for two subsystems we will get 2 A1 A2 matrix and 2 B1 B2 matrix and C matrix, which is common because our inductor, if you go back to the circuit, you will find this particular part is common, right. So, our C matrix will be same, C matrix will be same because it is associated with the output side dynamics. So, applying state space averaging technique that we discussed, first we have to obtain the state space average dynamics, then we have to consider the perturbation that we discussed already, then we have to find out the equilibrium point, and from here we can find out x equal to minus A inverse B into V in, and we discuss this is A, B and A is invertible. Then we can find out the linear small signal model, and this we have shown it can be very easily obtained by Taylor series. So, where we got A matrix to be is given us, I mean this all thing we can obtain. A matrix we have already shown, B matrix also we have shown. Okay. So, we talk about this is B1 2 and this is this whole thing to be B1 1, that we have already derived earlier. So, with this we can write down the full expression that we already wrote for a generic state space averaging approach. Then we can obtain control to output transfer function, we can obtain audio susceptibility and as well as control to inductor current transfer function. Now, interestingly you will find that A matrix is common for a buck converter, that means A, because if you take the individual subsystem except for this element, if we consider they are more or less same, then this A1 A2 both are same, that means your A matrix will be common. But if we take a boost converter, it is something different, where in a boost converter again we can take two sub interval 1, sub interval 2. In this case our switch, main switch is on and the complementary switch is off, and we can write down all the equations and then we can plug in to make the state space equation, where again we are taking x 1 to be I L and x 2 to be V c, the capacitor voltage. This is for mode 1 equation, and here it is the output voltage equation. In this case, the output voltage is not connected to the inductor current, it is connected to the capacitor. Output capacitor is connected, output voltage is connected to the capacitor and capacitor is discharged by the load current. But if we take sub interval 2, when the main switch is off and this auxiliary switch is on, that means complementary switch is on for a synchronous boost converter, again we can write down all the equations and then we can summarize the state space equation here using this state variable. In this equation, you will find the output equation is different, because here you have an additional inductor current term, because in this case output, when the switch is off, the inductor current is connected to the capacitor side. So, as a result the capacitor output voltage will have two, if you see the output voltage dynamics, C1 and C2 are different, and as a result at each switching, whenever the switch changes its state, there will be a discrete jump due to this jump, because there will be a term which is alpha RC I x 1, and x 1 is nothing but alpha RC into IL. When the switch is on, this will be 0, when the switch is off, the IL is connected. So, at every switching transition there will be a discrete jump in the output voltage due to this and non-minimum phase behavior, particularly the inductor current is connected and disconnected, and this will create a direct jump in the output voltage. So, the output voltage in a boost converter will have a discontinuous jump, whereas in case of buck converter, if you do not consider the effective series inductance ESL, then there will be no discrete jump, because ESR will only increase the ripple magnitude, but it will not introduce a discrete jump, but ESR in a boost converter will introduce a discrete jump. Now, you can write down the state space equation again. Here you will notice the A matrix are fundamentally different, two matrix, because these two terms are 0, but here it is non-zero, right. It is fundamentally different. Even though you take an ideal buck converter, boost converter, these two terms will make this A1 and A2 matrix are fundamentally different. But interestingly, here B1 and B2 matrix are common, because in a boost converter the input voltage is connected all the time. When the switch is on or switch is off, it is all the time it is connected. You see, input voltage is never disconnected from the inductor side. So, B matrix will be always here, in this case the same B matrix, but A matrix are different. So, if you take the state space average model, then again you can write down the average dynamics, you can find out, you can consider the perturbation and equilibrium point, and as I told, here again you can find out x equal to minus A inverse B V in, including this average, this average model. If you consider the steady state, this A matrix will be it is invertible. But if you take the individual A matrix, for ideal case A1 is not invertible, because it all elements are 0 except for the last element, it will be 0. If we go back to the equation, under ideal condition this term will be 0. So, all 3 elements are 0 except for this one, which is non-zero. But if you take the average A matrix, which is invertible, and again we can derive the linearized small signal model from this expression, using this expression. Okay, so, this will be again for our case B12, and for our case it is, this whole thing is B11. Okay. And the average dynamics for the boost converter will have, in this case this equation will be different, because we are talking about the output voltage, which is the output voltage average. If we take the perturbed quantity will be, what will be the perturbed quantity? It will have two components. One is, because for a boost converter you have a duty ratio dependency, C matrix are different. So, we will get 1 D into C1 plus 1 minus D into C2, this whole thing into x hat plus C1 minus C2, that into capital X, this whole quantity into D hat. So, output voltage will have two components. One is this term under steady state, and another is this term, and this will create a difference. So, this equation was actually it is just copied from a buck, but for boost it is the output voltage average dynamics. Small signal transfer function. So, in the small signal transfer function, again the same method can be used. We already found A matrix, B matrix, C matrix. So, we can obtain, we can write down the expression of the control to output transfer function. So, in this case we also found, that means if we do not consider any ESR, then these models are perfectly fine, and if we do not consider so we can obtain the transfer function of a boost converter for different switch configuration. So, here the C matrix is the equivalent C matrix, which is D plus 1 minus D into, what is this equivalent C matrix? Sorry. So, the same matrix that we obtained was C is equal to D into C1 plus 1 minus D into C2, that we can find out. So, you can derive audio susceptibility and control to inductor current transfer function. So, we will see in subsequent lecture what are the transfer function, how does it look like, and we also want to derive such transfer function using circuit averaging technique, and we want to compare that which one is accurate, whether they are same or they are different, and then we want to show the validation of the small signal model, both large signal and small signal model, and we want to match the response, time domain response of the actual switch simulation and the same thing obtained from the linear small signal model, and that we want to verify in subsequent lecture. So, with this I want to summarize that today we talked about state space modeling of switching power converters, switch mode power converters. We also obtained state space, we have shown state space averaging technique and large signal model, which is the average model. Then I have shown you how to find small signal model and DC operating points. So, with this we want to finish today's lecture. Thank you very much.